So this first part of the section is just a refresher on parametric curves. Remember we saw this in Unit 6, which is section 5.4 in the book. And there was a video, a Khan Academy video posted then. If you want to go back and watch that video, you are welcome to do so. We are going to go through an example here where we're going to sketch a parametric curve, but this is just to get an idea of what it looks like. After that, you don't have to draw each of these as you evaluate things, okay? So first of all, parametric curve is defined by multiple variables. Usually multiple is 2. Okay, because we're usually doing like a horizontal and a vertical, so x of t and y of t. And it's defined in terms of a third. That third is called the parameter. And this one, oops, forgot the 2. This one is usually t. Okay, you can think of it like t is time, but it doesn't necessarily have to be like minutes and hours and stuff time. Okay, so we've got x, we'll write it as f of t, and y is g of t, so it matches the notation in the book. I is the interval over which this exists, okay? Now, I didn't give an interval for this first one, but we'll still get an idea what it looks like. So one option for sketching parametric functions is to start by just making a table, just like you did when you first learned how to graph a line. You had like an XY table, and you'd pick values for X, plug them in, get your Y's, and then you'd plot those points. We're going to do that same thing with values for T. Okay, so we need a T column, an X column, and a Y column. So let's do the standard -2, -1, 0, 1, 2 and see what this gets us. So plugging these into these functions, we end up with when t is -2, x is going to be 2, y is -3. At -1, x is 0 and y is -1. At 0, x is 0, y is +1. At t equals 1, x is 2, and y is 3. And then at t equals 2, x is 6, and y equals 5. Okay, so then let's plot these points. Now, I'm plotting this on the xy plane. So this is x-axis, this is the y-axis. Okay, so we have a point at, here, let's count here. I need to go to 6, so 1, 2, 3, 4, 5, 6. Okay, so I have, no, hold on, I'm going to make that a little bit taller. 4, 5, 1, 2, 3. Okay, that's probably good enough. So 2, -3, put a point here. And then when t is -1, we have a point at 0, -1. And then at 0, +1, and then at 2, 3, and at 6, 5. Okay, so what we have, and I bet if we were to plug in -3, the fact that it looks like it's going to be symmetric, I bet we would land down here at 6, -5, okay? But what we have is we have part of a parabola that's opening to the right, and this isn't necessarily enough points to know that that's a parabola, okay? So I'm kind of making assumptions here, but it looks like we have something that is doing this, okay? And the problem, there, it's kind of close. The problem is that by just picking some integer values for t, we don't have a full picture of what this graph looks like. Like, for example, if this is actually a parabola, I don't have any way to figure out, just based on these points, I don't know where my vertex is. So I would need to guess some t values in between -1 and 0, because remember that's when we were here and here, maybe 1/2, maybe 1/4, something like that, to try and figure out what that point there is going to be. Okay. One other thing about graphing this is because it is parametric, the direction is represented by the increasing t values. So because we started down here, we put these arrows on the curve to indicate that the curve proceeds in this direction as t progresses, okay? But again, we have this general idea of what this looks like, but we don't know maybe the entire curve. And maybe we wouldn't have even gotten that close if, if these points were further apart to knowing where the vertex was. So another option we have is we can do what is called removing the parameter. And to do that, we're going to use basically a system of equations with our x and our y functions, and we're going to get rid of the t. Now, it won't show us the direction, but it will give us a better picture of the xy graph. So what we're going to do is usually substitution is the fastest way to do this. Not always, but in a case like this where we've got polynomials, substitution works well. So I'm going to take this function and solve for t. So I get t equals y minus 1 over 2, and then substitute that into the function for x. So I end up with x equals this whole quantity squared. Since I've got a 1/2, I'm going to write the 1/4 in front, okay? And then I've got y squared minus 2y plus 1, okay? So that's the t squared part, and then plus y minus 1 over 2. And let's see, so we've got distributing the 1/4, this would be y squared over 4. This would be negative 1/2 y. This would be 1 over 4. And this is y over 2 minus 1/2. Okay, so we end up with x equals 1/4 y squared. And then the this negative 1/2 y and the positive 1/2 y will cancel each other out. And we've got 1/4 minus 1/2, so minus 1/4 left over. Okay, so this, and I'm going to rearrange it a little bit more, is, let's see, 1 over 4 y squared. Okay, so this is a much better equation to look at because we know that this is a parabola. It is opening to the right, okay? And let's write this down. So this is a parabola. Oops. With a vertex at negative 1/4 comma 0. Okay, so negative 1/4 is really where that vertex should be. So I was kind of close. Okay. So for these next couple examples, we are going to just do a little practice rewriting from the parametric form into Cartesian form or XY form. We will do some examples where we specifically leave things in terms of the parametric functions, but for now we're going to do a little bit of practice going back and forth. So here we've got x is equal to root 1 minus t squared and y is equal to t, and then our interval is from negative 1 to positive 1. So a couple of options. One thing we can do is substitution like we did before. Okay, so since y is equal to t, that's going to be a pretty easy substitution. I'm going to put y in place of the t here. So we end up with x equals root 1 minus y squared. Okay, now I can do some algebra here and rewrite this as x squared equals 1 minus y squared. So hopefully we should recognize that form, but this is the same as x squared plus y squared equals 1. Okay, now this is the equation for a circle. Something we need to check though is this may not represent the entire circle. Okay, so we know that based on the way that it's written right here, we know that x has to be greater than or equal to 0. We also can plug the endpoints of the t values in to see what x could be and what y could be. So because y is equal to t, I know that the range of this graph is going to be, let me write this, so the range is going to be from negative 1 to positive 1, okay, meaning that y can be both negative and positive. However, if I plug negative 1 and 1 into the x function, I'm never going to get a negative output here, so my domain is only 0 to 1. Okay, so this is actually a semicircle, and it happens to be the right half of the semicircle. So semicircle with a radius of 1. Okay, and then for this next one, Here we have trig functions. Now, if you have trig functions, you should not be thinking about substitution, because using substitution here means we are mixing together the trig functions and inverse trig functions, and we don't really want to do that. So instead, we look for some relationship between this trig function and this trig function. First thing I want to do is rewrite this part without that 3. So I'm going to write this as sine t equals x over 3, okay, and then cosine t is y. And now I'm going to use a trig identity using the Pythagorean identity, sine squared t plus cosine squared t is equal to 1. I can use substitution now with my y and x over 3 and write this as x squared over 9 plus y squared is equal to 1, okay? And so this is my function. This is my second function, and this, as we remember, because we've reviewed them recently, is an ellipse. And I will go through the cycloid part here in a separate video.